Assalamu alaikum. I hope you're doing well. Today, I'm very excited to start this. Basically, today we are going to talk about calculations. And of course, one of the biggest topics that we have in calculations is moles. So we're going to start with that. And I'm very positive and very confident that inshallah, today you will not have any problem with moles or the topic as far as the calculations or stoichiometry is concerned after the lessons that we have for this week. So we have 4 days and our goal is mole. Let's get started. All right, so the first thing that we need to do for any calculations is first to talk about the particles that we are dealing with. So in chemistry, we know that we have atoms, right? That's where everything starts. So we have atoms, and atom has 3 subatomic particles. There is proton, I'm going to write as P positive, there is neutron, and there is electron. All right, now the two of them, protons and neutron, they're both inside the nucleus, and we have electrons outside. Now the thing with electrons is that they are very light. All right, so they're very light, and because of that thing, them being very light, that simply means that their mass doesn't really count. Their mass is negligible. In fact, if you added around 1800 to 1900 different electrons into one atom, only then will you have a difference of one, just one, in the mass of the atom. So basically the mass of electron doesn't really count. It's really small. It's almost 1840, or some people say 1846. We don't really have a very exact number, but that many electrons to weigh equal to one proton. So the two things that matter as far as the mass is concerned are protons and neutrons. Next thing is that if you have protons, if you have neutrons, then what is their mass? Now the thing is, their mass is also really small. In fact, we have a very small value for their mass, 9.11 into 10 power minus 31 even. So it's a really small value. The reason it is because our units kg is actually really large. In fact, gram is also very big. So for that reason, we can't really use grams for protons or neutrons. It's a really huge unit compared to what protons or neutrons are. So what do? We assign them their own new unit, which we call atomic mass unit. But in O levels and IGCSE, we don't really use that unit. We just say the number. So for that reason, we are going to say that proton of mass is 1. In fact, that is relative mass. And neutron is also almost 1. It's a little more than proton, but for our purpose, it would do. So the mass of proton is 1, mass of neutron is 1, and you add them together to get the mass of every atom. So let's say I have carbon 12. Now carbon 12, I say it's carbon 12 because its mass is 12. How do I know it's 12? Because it has 6 protons and 6 neutrons. So 6 plus 6, that's a mass of 12. So how do I know mass of any isotope? You know what isotopes are. They're atoms of same element but with different neutron number. So number of neutrons or neutron number. Let's say I have another one which is carbon 13 and another one carbon 14. Now they're all carbons. Why are they all carbons? Because they all have 6 protons, right? That is how they are atoms of carbon. But because they have different number of neutrons, that is why they are different mass of each of them. So one has 12, one has 13, one has 14. You can guess that one has 6 protons, 6 neutrons. The other also has 6 protons. It's carbon, right? So 6 protons again, but 6 protons with 7 neutrons, and then 6 protons and 8 neutrons. That's carbon 14, right? So that is how their masses are. Now here's the thing. If I say I have a carbon atom, what is its mass? I wouldn't be able to know without knowing how many protons there are, right? Because I need to know what isotope I have to exactly know which isotope it is, right? So for that reason, it doesn't become very efficient to talk about any atom or its mass, because then you have to talk about isotope, and if you have many different isotopes, then the mass of every molecule is going to be very different. I'll give an example. Let's say I have H2O. Now it has 2 hydrogen and 1 oxygen, right? But hydrogen comes in 3 different isotopes, hydrogen 1, hydrogen 2, hydrogen 3. Similarly, oxygen comes as oxygen 16, oxygen 17, oxygen 18. So just knowing mass of this water molecule is going to be quite a mess, because I can have hydrogen 1, hydrogen 2, hydrogen 3, oxygen 16 managed with that. One has hydrogen 1, one has hydrogen 2. There's so many combinations that I can get. It can get really confusing, right? So what do chemists do? Do they all day just go on calculating different isotopes and figuring out what their mass is? Actually, no. What they do is that they take out the average. And we take a special kind of average which we call, sorry about that, we call it a weighted average. Now, what's a weighted average? You guys are in O levels, right? Or IGCSE. Now, you are going to have 3 papers. One is paper 1, one is paper 2, one is paper 4. And IGCSE people are going to have paper 2, paper 3, paper 4, paper 6, depending on what combination you have. Are you going for core or are you going for extended? So just to summarize, we will have an MCQ paper, a theory paper, and at the end we will have an ATP paper, right? Now, let's say the examiner says that, all right, somebody got a result. In the MCQ paper, they scored 30 out of 40. In a theory paper, they scored 60 out of 75. And in the ATP paper, they scored 52 out of 60, right? So what's the total percentage, total marks? I just add it all up, right? That's what we will do if we were just taking out the average. So we will add 90, 30 plus 60 plus 52, that is 142, and divided by the total, which is 175. And then we will know what the average is going to be, right? We'll simply take that. Just give me a minute to get the calculator. Yeah. So we have 142 divided by 175 and times 100%, that is 81.1%. So that's the score of this guy, this student, right? Now here's the thing. Examiner doesn't always work like that. Examiner, in fact, gives you some weightage. Now I'm just making it up. I'm just making the percentages up. I don't have the exact percentage. So don't take that value. So let's suppose MCQ goes for 30% of the paper, ATP goes for 30% of the paper, and theory goes for 40% of the paper, right? So now you can't just say, oh, it's 81.1%, because 81.1% is out of 175. What we have over here is not that. What we have is basically a percentage thing. We have to calculate the weight of every paper, the weightage of every paper. So how do you do? So you just take 30 over 40 for the MCQ one, multiply by 30%, because that's its weight. Then you take 60 out of 75 of the theory paper, multiply by 40%, and then you take 52 out of 60 of the theory paper and multiply by 30% again. When you get all of that, you just add it up. Give me a minute, let me get my calculator. Yeah, here we have it. All right, so I'll just take that 30 divided by 40 times 30%. I can also just multiply by 0.3 to get the same answer, plus 60 over 75 times 40%, plus 52 over 60 times 30%. And I take that, my average comes out to be 80.5. So now the weighted marks of this student is actually not 81.1, it's 80.5, because this student lost more marks in theory, so they had a disadvantage because of that. This is called a weighted average, and that is exactly what we do with different isotopes. So let's go back to that. Let's suppose I have these 3 different isotopes of carbon. All right. Now let's say I want to know what my average mass of carbon is. Like you take any carbon atom, what's its average? So for that, I need to know what percentage of different isotopes is there. So let's Google that, carbon isotope percentage. This percentage is actually called abundance. All right. So if we do that, here's a rough idea that we get from UMD's website. So it says that carbon 12 is accounting for roughly 98.9% of carbon in the world, and carbon 13 is going for roughly 1.05%, and the remaining is obviously 0.05%, which is for carbon 14, right? So there you go. That is the percentage differences. I'm going to, this one is called abundance, the percentage, the weightage of every isotope. All right, now this is given in the exam. You don't need to worry about how to calculate it or how to figure it out. There is a technique called mass spectrometry that we use for this, not in O levels or IGCSE. All right, so let's calculate the mass, the average. Now, just like in exams, you were taking the score of your theory paper or MCQ paper and multiplying by the weightage, we are going to take the same thing. We're going to multiply the mass of this isotope and multiply it by its percentage. Now, because it's percentage, I have to divide by 100 at the end. Similarly, this one I'm going to take 13 times 1.05. Why is 1.05? Because 1.05%. And then 14 multiplied by 0.05%. And that is my individual score, right? Individual weighted score. I add them all up and I divide them by 100% to figure out that my average mass is going to be so we have 12.0115, but I won't take that because my original values are to 1 decimal place or 2 decimal place. I'm going to just take it to 2 decimal place as well. So 12.01 is my relative atomic mass. This is my weighted average. So we call it relative atomic mass. All right, so that's what it is. What is relative atomic mass? It is the average mass. So here's the definition. They can ask you for the definition for 2 marks. So what is the relative atomic mass? It is the average mass of all naturally occurring isotopes compared with, now so far it's good, right? Compared with 1/12 of carbon-12 atom or isotope. Wait a minute, what? So you are saying that you have weighted average, sure, or average mass, sure, that's fine, makes sense. What is that last part? Compared with 1/12 of carbon-12, like what? So basically the idea is that you're going to assign them some weightage, some unit, right? So that unit, the word unit means 1, right? So if we are going to take a unit, we have to base it on something. kg is based on 1 kilogram that somebody made up, and then we are all following that, right? Just like that, carbon-12 is the standard atom that these scientists selected for a bunch of different reasons. Now, the mass of carbon-12 is 12. It's not 1, but I want a unit. So how do I get that? 1/12 of 12 is 1, right? So that's the logic behind it. That you take 1/12 of 12 and that's 1. So now you have your unit and you can compare everything with that. So in the exam, this will account for 1 mark and this will account for the other mark. And usually they ask the definition and they ask you for 2 marks for this. All right, so that's relative atomic mass. All right, so I have relative atomic mass. Now I can weigh different atoms. So what about if I have many different atoms in a molecule? Let's take an example. Let's say I have H2SO4, hydrogen sulfate, or if we dissolve it in water, it's sulfuric acid. All right, so let's count how many atoms I have. I have 2 hydrogens, 1 sulfur, 4 oxygen. All right, so the total mass of H2SO4 is nothing but summing up every individual mass and you have the total mass. All right, so I'll just add them all up. 2 times 1 because my mass of hydrogen, the relative atomic mass is 1. Where do you get that value? You check your periodic table. I've already shared the standard, the official periodic table that we get in the exam with you. So make sure that you use that in your all your practice, sorry. All right, sulfur, that is 32.1, but we'll take the value of 32. Similarly, oxygen is 4 times 16. Why 4 times? Because in one molecule of H2SO4, I have 4 oxygen. So that's why I multiplied. Now I add it all up, I get 98. So mass of one H2SO4 molecule is 98 atomic mass units. When carbon is 12, so this is 98. This is almost what? 8 times? Yeah, a little more than 8 times the mass of carbon 12. So this is a really heavy molecule compared to, for example, hydrogen. Hydrogen is just 2 hydrogen atoms, and that is what? Just 2 hydrogen. That is 2 times 1. The mass is just 2. 6 of these make 1 carbon 12, and more than 8 of that carbon 12 will weigh equal to H2SO4, 1 molecule. So H2SO4 is a big molecule. Alright, so this way you can weigh different molecules, and this thing we call it MR. MR is when you add all the individual ARs of every atom that is there, it's the average mass of every atom that's in there, and you add them all up, you get your MR. And interestingly, and this is a very important part, you take MR, grams of anything, and you get 1 mole. Just take MR grams of any chemical in the world, and you're going to get 1 mole. And that's what mole is. At the heart of it, that's what mole is. How do you weigh mole? You simply take MR of that thing and you take that many grams. I can weigh all the grams. I can just take the balance and put it on there, and when I have enough, that's my MR grams, and that is 1 mole of the thing. So 1 mole of hydrogen, 2 grams. 1 mole of sulfuric acid, 98 grams. 1 mole of carbon, 12 grams. But why do I need a mole when I already have MR? Why am I calling it a different thing? Because 1 mole is a way for us to count the particles that are in there. I want to know how many atoms of hydrogen, or how many atoms of carbon, or how many molecules of H2SO4 are there in 98 grams. It's really difficult. But with mole, it becomes actually really easy. Why? Because 1 mole uses a special number that we have. You know, numbers have names. For example, this number is 100. This number is a big number. This is a million, right? These numbers have names. This number, it also has a name. We call it 12, but 12 of anything, we call it a dozen, right? So this is a number which has practically a different name. So just like that, there's a big number that is 6.02 times 10 power 23. It's a big number. It has 21 zeros after that too, if you were to write it all expanded form. But this number is called Avogradros number, named after Emilio Avogadro. So this is Avogadro's number. And here's the thing. Why do I need mole? You take 1 mole of anything, and you know how to take that, right? You know, you just take MR and that many grams, right? And that will have exactly Avogadro's number of particles. So what is 1 mole? 1 mole of anything, or 1 mole, let me define it. So 1 mole of a substance is the amount. 1 mole of a substance is the amount with Avogadro's number of particles. So basically, what's a mole? You take 6.02 into 10 power 23 particles, and that's 1 mole. Just like you take a dozen of anything, and that's 12, right? I did not have to tell you that it's 12. I just said it's a dozen calculators, and so you know it's 12. It's a dozen AirPods, that's 12 AirPods, right? Just like that, if I have a mole of anything, a mole of AirPods, that would be Avogadro's number of AirPods, 6.02 into 10 power 23 of these things, right? In fact, there is not enough substances or not enough material in the world to make that many AirPods. So it's a really huge number, but it's actually really easy to calculate. You just know that 1 mole of anything is that many particles. Okay, and how do you weigh it? Simple, MR grams. There you go. But what if I don't want to weigh it? What if I want to get the volume of that gas? I'm working with gas, it's really difficult to weigh it. I want to measure the volume. No problem. Mole gives us a shortcut for that as well. Turns out, if you take mass of 1 mole is mR grams. But if you take volume of 1 mole, again, it's a gas. If you take volume of 1 mole of gas, it's going to be 24 dm cube. But you have one fact that you have to remember. You know, at different, if I have, say, different temperature or pressure, gases expand, gases contract, all of that. So for that, we have to make sure that we're using room temperature and pressure. All right. So at room temperature and pressure, any gas, and it doesn't matter what gas it is, that's the power of mole. It's so universal. Any gas you take, carbon dioxide, methane, or boil some water, that will be 24 dm cube at room temperature and pressure. Exactly 24 every single time. And that's remarkable. Okay, what if I don't want to take that? I want to actually know how many atoms are there. Sure, that's 6.02 into 10 power 23 particles. See, so mole is basically a very simple way for us to know what the mass of something is, what the volume of that gas would be if I boil it, or if the gas is already there, and also to figure out how many molecules of that thing I have. Okay, so let's go back to our example of sulfuric acid. So what is it telling me? 98 is the mR of sulfuric acid. So 98 gram is 1 mole. And how many molecules will it have? 6.02 into 10 power 23 of those things. Okay, and if I boil that H2SO4, what will be the volume of that gas? Oh, it's simple. The volume is going to be 24 dm cube. Exactly. Okay, what if I don't have that? What if I have, let's say, 50 grams of H2SO4? What will be the volume of that thing? Now, if you don't understand mole, it will be really difficult to figure that out. But with moles, we have a really, really easy method. It's called ratio method. So here's what I'll do. I know that 1 mole of sulfuric acid is 98 grams because its mR is 98 grams. And its volume, if I boil it, will be 24 dm cube. Okay, so if I have 50 grams, what would its volume be? X. There you go. Cross multiply, and there you have it. 98x equals to 24 times 50. X is going to be 24 times 50 over 98. And what do we get? Oh, it is 12.2 dm cube. There you go. See, that's the power of moles. Now, this is a very helpful method, and this is special for me personally because, you know, I did not get moles when I was studying chemistry in O levels, and I would really struggle with it, and I was asked to just memorize the formulas and apply them, and they didn't work with me. I wasn't comfortable with those formulas. So I was just a student like you in grade 10, I think. That's when I first learned about moles, and this is the method that I came up with just for my own understanding. Of course, I couldn't use it in my school because, of course, you know, teachers expect formulas, and at that time I thought examiner also expects me to write formulas. So when I grew up and I became a teacher, so I was at a conference in Islamabad and one of the examiners from Cambridge was there. So I showed this method to them, and I was like, can we students use this in the exam? And it was like, yeah, sure. And I was so happy. I was ecstatic because this is something that I'm really proud of. I know it's a really simple maths, nothing fancy going on, but I'm really proud of this method, to be honest, because it works. In every single question that I've seen in moles for O levels, A levels, or even beyond, it works. It's really, really simple. I'll do it again. Another problem. Let's do it. So here's a question. We boil 200 grams of water. All right. What is the volume of steam that we get? So here's the question. We have 200 grams of water and we're boiling it out. So what do we have? We have water, right? So H2O. All right. What's its MR? Let's calculate that. I have 2 hydrogens and 1 oxygen. Okay. So 2 times 1, that is 2 hydrogen, plus 1 times 16, that is 18 in total. 18 is the MR. So what's 1 mole? 18 grams. There you go. So what is 1 mole of water? 1 mole is MR grams, which is 18 grams. And if I boil it, it will be 24 dm cube. Great. So I have 200 grams. Okay. What will its volume be? X. Cross multiply. X is gonna be 18 times X is 24 times 200. And I bring this here or divide both sides by 18, depending on how you were taught basic arithmetic. And there you go. Let's do it. 24 times 200 divided by 18, and you have it. 267 to 3 significant figures, decimeter cube, and there you go. 267 dm cube is the volume if you boil 200 grams. And you see how remarkable that is. 267 liters is a huge volume, and we are boiling water that is less than 1 glass of water. All right. So you see how the factor with which these gases expand when you heat them up or when you boil these things. So yeah, there you go. Now, what if I don't like this method? And that's a perfectly valid thing to do. What if I still want to do formulas? Let's suppose I'm a student who's comfortable with formulas, and for some reason my teacher also demands me to write formulas. There's nothing wrong with it. There's nothing wrong with it. All right, so what do we do? No problem. Remember that these formulas are all made from the same idea, that 1 mole is mR grams. So X moles will be whatever mass you have divided by that. All right, so let's do it. So what do I want to do? Let's say I have, we talked about dozen, right? So let's say I know that a dozen calculators would be 12 calculators. So what if I have 20 calculators? How many dozens is that? So all I got to do is divide 20 by 12, and I know how many dozens it is, right? I'm just dividing it by 12 to figure out groups of 12 that I'll take. So just like that, what is 1 mole? Mole for mass, it is mR grams, right? So 1 mR is 1 mole. So if I have a given mass, divide that by mR, and I have the total number of moles that I need. All right, so I have moles. It is mass over mR. Why is it mass over mR? Because I'm dividing everything in terms of the mass of 1 mole. Because here's something in the formula that you're not looking at. You have 1 mole. So on the left side, what is it telling me? The X moles, or whatever number you want to get, weighs this much, when 1 mole weighs this much. See, the formulas come from the definition. So I'll just ignore this, and there you go. I just hid it. So this hidden 1 is the key to understanding this and why these formulas work. All right, what if I have gas volume? All right, so gas volume divided by 24, that's moles. Again, the hidden thing is 1. That 1 tells me that 1 mole is 24 dm cube. X moles is this gas volume. Sure, no problem. So let's do that same problem. We had 200 grams of water that we boiled, and we want to know what will its volume be. Let's do it with the first formula. I have 200 grams of water. So I'll start with the first formula, that it's 200 divided by 18 to figure out how many moles I'll get. Okay, it's 200 divided by 18 is 11.1 mole. Okay, that is the number of moles of water. Now what will its volume be? The steam. So now I plug that in here. So 11.1 is going to be gas volume, whatever it is, over 24. This multiplies here, or you multiply both sides, again, depends how you studied basic arithmetic. And there you go. I get gas volume is going to be 267 dm cube. Exactly the same. Because the definition we're following is exactly the same. So here's how you convert things. Moles, you need to know what you're converting moles from and what you're converting moles to. You can have mass, you can have gas volume, you can have number of particles, you can have concentration and volume, which we'll talk about later on. So whatever information you have, take that formula, take your pick. If I have number of particles, I'll divide them by Avogadros number. Why? Because Avogadros number is mass or number of particles for 1 mole. So that one, let's hide that. So the formula is easier to remember. So moles is number of particles over Avogadros number. And that will tell you the molecules or the particles or ions or whatever you have. Clear? So this was our first lesson on moles. I'm going to share a worksheet with you on mole conversion and learn how to. So we learned how to figure out the AR, we learned how to figure out the MR and how we can use that MR to figure out mole and convert that to find volume, to find number of particles, to basically master calculation. So whether you use ratio method or whether you use formulas or whether you have your own method, if you have one, please share with me. Post in comments or just WhatsApp it to me and I'll be happy to share that with the class over here as well. Alright, so I'm going to give you another worksheet for this mole conversion. Make sure that you do it, and if you have any questions, let me know. If you understand this, I'll be really happy. And before you go, hit that red button for subscription and I'll see you in the next class tomorrow. Allah Hafiz.